Hello everybody and welcome to Bash Course Quarantine Physics 2. My name is Young Hank and today we're going to learn about electrostatics. Let's start off with the absolute basics, charge. Fundamentally, everything in the universe has some mass. When we talk about kinematics, the mass is affected by forces and accelerates, and has speed. When we talk about electrostatics, we worry instead about charge and how that affects potential and field, and attraction and flux. The charge of an object is represented by any real number, positive or negative. The unit for charge is coulombs. Electrostatics is the study of charges at rest. One important thing to note is that, like mass, for charge there is conservation as well. The law of conservation of charge states electric charge can neither be created nor destroyed in a closed system. The amount of charge remains the same. When something changes its charge, it doesn't create charge but transfers it. Now, the way we often see charge at school is related to chemistry with electrons and protons. This is very relevant. All charge comes from some unbalance of electrons and protons in a substance. Protons are much bigger than electrons, yet they have the same fundamental charge associated with them, one positive, the other negative. We represent this fundamental charge with E. When we talk about charge, there are two types of materials, insulators and conductors. An insulator does not allow for electrons to move around, while conductors do allow movement. When charge moves between two objects, that is called conduction. In that case, electrons actually move from one surface to another. Induction, on the other hand, that is sort of like dipole-induced dipole forces. It works by the electrons on one object moving relative to a charged object nearby. This means that neither of the two are actually changing their net charge, but they are changing their distribution of charge. One common tool used to measure the charge of something is an electroscope. It involves two thin gold leaves on the end of a conductive rod. When a charged object comes near the top, electrons will move from one end of the electroscope to the other, causing a high charge in the leaves. Because both of the leaves have the same charge, they repel, and you can effectively measure the strength of the charge of the object based off of how much those leaves repel. You might be wondering why they repel. We can derive that fact from Coulomb's law. The law states that Fe equals kqq over r squared, or that the electrostatic force is directly proportional to the magnitude of the charge on both of the objects and inversely proportional to the distance between them. This relationship is turned into an equation by adding the constant of proportionality k. Coulomb's constant, 9 times 10 to the 9th newtons meters squared per coulomb squared. Alright, so let's look at this example problem. There are two charged point masses 10 centimeters apart. One of them is positive 6 nanocoulombs and the other is negative 7 nanocoulombs. To find the force between them, what we're going to do is we're going to plug in those charges in that distance. So we have 6 times 10 to the negative 9th coulombs, times 7 times 10 to the negative 9th coulombs, that's a negative 7, and times 9 times 10 to the 9th, and that's the k, and then we divide by 0.1 squared. That's 10 centimeters squared, but we have to put it in meters. When we add that all into our calculator, do the multiplication, the division, we get 3.78 times 10 to the negative 5th newtons. And because it's negative, we know that they're attracted to each other. An electric field is a region around some charged thing within which something else charged will have a force acted upon it. The equation for electric field is E equals kq over r squared. It's measured in newtons per coulomb. Alright, so let's look at this second example problem here. If we have a charged point mass of negative 10 nanocoulombs, we're looking for the field strength 20 centimeters away. Now the way we're going to do that is we plug it into our equation, kq over r squared. So we have 9 times 10 to the 9th, k, times negative 10 times 10 to the negative 9th, that's q. Then we divide by 0.2 squared, that's r squared. When we do that math in our calculator, we're going to get negative 2,250 newtons per coulomb. Electric fields can be drawn as electric field lines around charges. These lines begin at positive charges and end at negative charges, and are denser where the field is stronger. A parallel plate capacitor is two parallel plates set up with opposite charges. In its ideal form, it generates a uniform electric field. But in reality, the field is warped at the plate edges. This is called the fringe effect. Charge sits on the outside surface of a conductor, so the electric field within the conductor is zero. Outside the conductor, the electric field is always perpendicular to the surface of the conductor. When the surface is flatter, the electric field is less dense. Electric flux is the measure of the electric field perpendicular to a surface, with the equation phi equals Ea cosine theta. The units for flux are newton meters squared per coulomb. Gauss's law states that charge in a surface correlates proportionally with the electric flux through it. This is represented by phi equals q over epsilon naught. Epsilon naught is a constant known as the permittivity of free space, or vacuum permittivity, and is equal to 8.85 times 10 to the negative 12th coulombs squared per Newton meter squared. It can also be related to Coulomb's constant, where k equals 1 over 4 pi epsilon naught. Let's give it over to Faith for a quick derivation of the equation for electric field from Gauss's law.
Thanks, Hank. Okay, get excited, guys, because today we're going to be deriving the equation for electric field from Gauss's law. So we have our two equations for electric flux. Phi equals EA cosine theta, and phi equals Q over epsilon naught. And we're looking for the equation for electric field, which is E equals KQ over R squared. So let's equate them. EA cosine theta equals Q over epsilon naught. Now isolate E. E equals Q over epsilon naught, A cosine theta. And here comes the tricky part. We can determine that A cosine theta is equal to 4 pi r squared, because the portion of the area that is perpendicular to the radius is just the surface area of the sphere around the point charge. So substitute that in. E equals Q over epsilon naught, 4 pi r squared. And since Coulomb's constant K equals 1 over 4 pi epsilon naught, we can substitute in K and get E equals KQ over R squared, the equation for electric field. Back to you, Hank.
Electric potential energy is the negative of the work done to move a point charge from one position to another. Delta PE equals negative W and is measured in joules. Now, as you should know, work is the amount of energy exerted when moving something a distance. In electrostatics, that work is done by an electric field. That field, when it is constant, like between parallel plates, does work equal to QED, the charge of the affected object, the strength of the field, and the distance. This is worked out by knowing that work is force times distance, and the field times charge is that force. Moving along to voltage, you've probably heard the word volts related to batteries. Electric potential or voltage is the measure of the amount of work needed to move a charge from one location to another in an electric field, but without taking into account the magnitude of the charge being moved. Like delta H for gravitational potential energy, delta V is a quality that relates only to position within an electric field of a certain strength. This is expressed by the equation delta V equals ED. Voltage is the measure of electric potential and is also found as KQ over R. Electric potential is the amount of work needed to move a single unit of charge, and so its units are joules per coulomb. Positive charges go from high potential to low potential. Negative charges do the reverse. Continuing with our gravitational analogy, when you look at a topological map, you can see lines that represent all points at the same elevation. With electrostatics, we call the lines of constant potential equipotential lines. When those lines are closer together, that signifies that the field is stronger. Note that field direction is always perpendicular to equipotential lines. Alright, let's look at this example on PhET's Charges and Fields lab. Okay, here you can see I have a positive charge up here and a negative charge down here, okay? And then in between, I've labeled a bunch of different equipotential lines. This straight one through the middle, that's at about 0 volts. And every line coming off is 1 volt higher this way and 1 volt lower this way, okay? Now, the thing here to note is that on a topographic map, when you have real close lines together, that signifies a really steep part of the map, okay? On an equipotential map like this, that's going to demonstrate a really strong field. So in the middle here at 0 volts, we're going to have that much. But as we get into steeper and steeper territory, that field's going to increase a lot, okay? So that's why that is happening. And you'll see that it's always perpendicular to these lines, no matter where we are. Now, you can see there that right there, down here it's not perpendicular, but that's because you're perpendicular to the equipotential line that the sensor is at, okay? So when I'm down at the 0 mark, it's perpendicular to that line, and it stays perpendicular there. When I'm out here, it stays perpendicular to the ring that I'm going around on. One last thing to do with electrostatics before we go, capacitors store charge. They are most simply made with two parallel plates of conductive material separated from each other. When electrons are shoved into a capacitor on one side, they repel the electrons off of the other plate. This stores the charge on the negative side. If you bridge the two sides of the capacitor with another piece of conductive material, that will discharge the capacitor. The electrons on the negative plate shoot through to the positive one. The measure of a capacitor is called capacitance and is measured in farads. We calculate that value by multiplying the dielectric constant kappa E naught in the area, and dividing by the distance between the plates. Capacitance is useful for knowing how much charge you can store on the plates. All you need is the equation Q equals CV, which relates to the charge stored, the voltage across the plates, and the capacitance. I mentioned the dielectric constant earlier. That value is based off of the capacitor's dielectric. The dielectric is the material that is separating the two plates. If it is just air, then that constant is 1, but otherwise you'll get some number other than that factors into the aforementioned equation. There's a way to measure how much potential energy is stored in a capacitor. You do half QV to get the stored potential energy. You can then substitute CV in for Q based on the equation before, Q equals CV. This will leave it at half CV squared for electric potential energy. That is all for electrostatics for now. Thanks for watching Bash Course Quarantine, and we'll see you next time. Stay out of school, kids. The Bash Course Quarantine team is Sam Mencimer, Eamon, Estela, Millan, Pasha, Ishaq, Sarah Orozco, and myself. Please put any questions you may have in the comments below, and we'll do our best to answer them or find someone who can. Thanks for watching Bash Course, and as they say in my hometown, oh my EOSH.